In this section we will discuss direct conversion receivers and the issues involved with DC offset, automatic gain control, and the IQ imbalance or mismatch. Direct conversion receiver is not the only way to architect a RF receiver for 802.11a, but we will focus on it in order to highlight some of the effects like DC offset and AGC and IQ imbalance and how to combat them. Here we show the architecture of a direct conversion receiver in a very simple block diagram form. The key component, of course, is after the antenna is the low noise amplifier that has to have a very small noise figure and relatively high gain. After the LNA, we have two mixers, one for the in-phase channel and one for the quadrature phase channel. We have a synthesizer that produces an in-phase term and a quadrature phase term. The filters filter out the double frequency terms, and we also have gains in the in-phase path and also gains in the quadrature path. We've simplified things here. We'll actually show variable gains for the control via AGC. This diagram is to just illustrate the operation of a direct conversion receiver. Here we show in the frequency domain a number of spectrums, signals with different frequencies, different carrier frequencies and different color schemes. The signal that we are interested in is illustrated in red at a carrier frequency, for example 5.2 gigahertz. In this case, the synthesizer would be set to 5.2 gigahertz. Now the synthesizer itself can be employed in many ways, but in a direct conversion receiver we're showing that the actual carrier input to the mixer is going to be, for example, 5.2 gigahertz, which is the channel of interest. After down conversion with the mixers, we see that at the receiver we filter the signals and we have our desired channel. We also show that you have a relatively large DC component. This is always going to be present in a direct conversion receiver, and we'll discuss methods for eliminating it. We also show that the other channels, the adjacent channels to the in-band channel, the desired channel, are also present because in a direct conversion receiver the actual baseband analog filters are such that they allow some of the adjacent channel to pass through, and the reason for that is we don't want to implement complicated filters in the analog domain or the baseband domain. If the filter was to actually eliminate the adjacent channel, these filters would be, first of all, they would need precision components. It would be difficult to match them between the I and Q channels, and of course they would consume a lot of area and power in order to meet the stringent requirements to eliminate the adjacent channel. The adjacent channel will be eliminated in the baseband digital single processing stages using decimation filters, where we can afford higher digital complexity, and that's a trade-off between the analog baseband and the digital baseband single processing, and we will discuss that in a whole separate topic. In a direct conversion receiver, one issue that will arise is IQ mismatch or IQ imbalance, and that occurs for a number of reasons. One is the fact that you have unequal gains on the in-phase channel receive chain and the quadrature phase channel receive chain, so you might have imbalance in the gains. In the synthesizer shown here, you can have a gain mismatch between the in-phase component of the cosine of 2 pi FCT and the sine of 2 pi FCT over here. You can have a gain mismatch. You can also have, even more detrimental, a phase mismatch between the in-phase and quadrature phase modulator, or in this case used to demodulate. And we'll get into that and see what the effect of both the gain mismatch and the phase mismatch is on the IQ imbalance. In a direct conversion receiver, the IQ imbalance is even more pronounced because in a heterodyne type receiver, most of the gain is done before the down conversion to baseband, but in a direct conversion receiver, after you down convert to baseband, you go through multiple gain stages. and these gain stages can exacerbate the IQ imbalance in the gains. Also, a big problem with direct conversion receiver is DC, and the DC can be amplified by the gains, the high gains in the baseband chain, analog chain, for the I and Q channel, and that can also cause an imbalance. Here we show the receive architecture for a Heterodyne receiver. This was actually published by Atheros, system on a chip for 802.11g in December 2005. And the differences with the direct conversion receiver are as follows. First of all, the down conversion is split into two stages. At the first stage, we down convert by 2/3 of the RF carrier frequency. Then we have the IF state where we down convert to baseband with 1/3 of FRF. Notice that FRF is generated from 2/3 of FRF through a divide by 2 implemented with flip-flops, so that the I and Q signals are actually in quadrature, so we don't have a phase mismatch between them. And that, of course, is very important in terms of eliminating IQ mismatch. The basic problems with IQ mismatch here would be due to the different gains within the receive path for the I channel and the Q channel. Also, in the case of the Heterodyne receiver, you can have higher gain stages at the first down conversion process and have less gain in the baseband gain stages, and therefore have less IQ mismatch potentially. And also, the DC, while present, is not as large as in the case of direct conversion receivers. So there's a lot of trade-offs between using direct conversion and also a Heterodyne receiver architecture. Again, we show the architecture of a direct conversion receiver, of course simplified. And what we want to discuss are some of the issues related to direct conversion receivers, in particular DC offset. Here we show a number of mechanisms in which DC offset occurs with a direct conversion receiver. First, a few more points about some of the benefits of a direct conversion receiver, and then we'll discuss some of the DC issues, DC offset issues. In a direct conversion receiver, notice that most of the filtering, the bulk of the filtering, is moved to baseband using analog baseband filters here, and therefore we eliminate the need for bulky precision filters at higher frequencies. And given monolithic integration, it is easier to match components in a monolithic integrated circuit. One more thing is that direct conversion receiver is more appropriate for a monolithic integrated circuit rather than discrete components because of the difficulty in matching components in a discrete implementation. And typically you would, if you do a discrete implementation, you may prefer to use a Heterodyne type receiver architecture. In this slide we show some of the mechanisms that generate DC offset in a direct conversion receiver. Here we show the fact that when you have the oscillator, local oscillator, the LO, mixing with the incoming signal, due to the fact that the LO is not isolated 100% from the mixer, and the fact that some of the LO might leak through the LNA, especially the LNA has a high gain, and you have what you call self-mixing over here. And this will produce a DC component. Here we show the LO, for example, at cosine 2 pi ft, and f is for example, the carrier frequency. And due to the fact that we are not completely isolated, you would have LO leakage shown by the component alpha, so you'll have self-mixing, where the LO mixes with alpha times the LO oscillator frequency. And if we use a trigonomic identity for cosine squared of the angle, we get the baseband term and also double the frequency term over here. The double frequency term would be filtered out. However, we do get a baseband term whenever we got cosine squared of theta. That can be expressed as 1/2 1 plus cosine of 2 theta. The 2 theta component contributes to the second harmonic, which is filtered out. However, the baseband component here contributes to a DC term. So we have a DC term due to self-mixing from the LO, and lack of isolation between the LO and the mixer, and of course we have the LNA with a strong amplification where we have a leakage from the LO to the front of the LNA. It gets amplified and we have self-mixing. Any self-mixing would lead to a DC term. Other contributors to DC offset are the strong interferer, for example. In the case of a strong interferer, it would pass through the LNA and also leak into the branch for the mixer from the LO to the mixer and self-mix with itself, also contributing to a DC term. So strong interferer is also a problem causing DC offset. Another potential cause of DC offset is when it radiates out through the antenna and is reflected back to itself, then you have self-mixing again and the potential for DC offset. In a direct conversion receiver, it is very difficult in a monolithic integrated circuit to isolate the LO from the mixers so that you don't have self-mixing, so that alpha is very small. And that's one of the reasons why the LNA would also be put off chip. That would be a reason to put the LNA off chip in order to isolate the local oscillator from the LNA, so that you don't have this situation here where you have LO leakage through the LNA and you have self-mixing. If we go back to the direct conversion receiver architecture, typically you have very high gain stages in the baseband versus the case in a heterodyne where you have a high gain prior to demodulation back to baseband. And therefore any DC generated due to self-mixing would go through amplifications in the baseband and cause a large DC component at the input of the analog to digital converters. And this DC offset has to be estimated and compensated for by the baseband digital signal processing and fed back to the analog front end and eliminated. Here we show the DC compensation for the Atheros system on a chip for 2.4 gigahertz, and you see that there are feedbacks from the baseband digital signal processing back into the analog front end. In this case, the baseband estimates the DC and puts a digital code into the digital to analog converters that then subtract the DC component at the various stages on the receive path. So this is a typical way of eliminating the DC, especially prior to the high gain stages, with a coordination between the RF front end and also the digital baseband signal processor. The baseband digital signal processor also has to take into account that the amount of DC that has to be fed back and eliminated is also dependent on the gain. Therefore, there could be table lookups that associate different DC offset controls versus the actual gain. A similar mechanism will be used in a direct conversion situation, except that in the direct conversion, DC is more of a problem and added measures have to be taken. A very important topic in direct conversion receiver and also in heterodyne type receivers is automatic gain control. A very important issue in 802.11a, 802.11g, and in Wi-Fi and WiMAX in general. This diagram here shows the mechanism for AGC in a direct conversion receiver as published by the folks at IMEC. This was back in 2002 in a paper called OFDM WLAN Receiver Performance Improvement Using Digital Compensation Techniques, in which a number of issues dealing with AGC and also DC offset and IQ imbalance compensation in the baseband digital signal processor are addressed in this paper. And we'll go over this very briefly and then show you a more simplified diagram. We have the basic LNA, an RF filter, we have a RF VGA gain, and then we go through the mixers. We have the VCO, we have the in phase and the quadrature phase, and we have filtering in the baseband, broken up into two separate stages with a baseband variable gain amplifier inserted in between, and we have the analog to digital converter. Once the signals are converted to digital domain in the baseband digital signal processing, operations are performed in order to control the gains of the RF front end and the baseband analog front end. AGC is normally done on the first 2 microseconds of the preamble using the short symbols, And once AGC has converged, frozen, and locked during the operations on the remainder of the preamble and, of course, the OFDM symbols themselves, the data symbols. Here we show that after the ADDs, basically there are some blocks within the baseband processor that control the AGC and feedback signals into the analog front end in order to control the gains both at the RF stage and at the baseband stages. This is a more simplified diagram adapted from the previous diagram. And one of the things we want to focus on are the baseband variable gain amplifiers for the I and Q channels, and also there is a variable gain amplifier in the RF stage. The variable gain amplifier in the RF stage has a separate control signal for the AGC than the baseband variable gain amplifiers. The baseband variable gain amplifiers are usually controlled over a range, and in this case they'll be in steps of 2 dB and from -8 to +8 dB. So the baseband variable gains can be changed from -8 to +8 dB in 2 dB steps with a digital control. The RF stage will be actually a 0-1 control, and you either have high gain or a low gain. Here we show diagrams that are basically adapted from the paper. Here we show the sensitivity for binary phase shift keying, and it's around 85 -85 dBm based on the standard. You also have the sensitivity for QPSK and also the sensitivity for 64 QAM or 54 megabits per second. Here we show the variable gain in dB. In the x-axis we show the RF input power in dBm, and it's very important to notice the sensitivity points. Now as we increase the signal power, we go across from left to right. In this region we're in the sensitivity range of both the BPSK and 64 QAM or 54 megabits per second. In the low SNR range, we set the RF gains and the baseband gains to the maximum level for the highest sensitivity possible. This has the benefit of having the highest gain for the low SNR cases. However, if we have a strong signal coming in, then we will exhibit saturation on the analog to digital converters and also saturation in the receive chain. In that case, we have to start peeling off the gain when we have high signal to noise ratios. So initially for high sensitivity we set the gains to maximum. However, when a signal with a high signal noise ratio arrives, we have to immediately start peeling off gain, and that is done by observing that the A to D would start to saturate, or we have a threshold for the RMS at the A to D output. So the baseband processor is continuously calculating the RSSI, or the average power at the output of the A to D, and if it exceeds a certain threshold, it realizes that the gains are too high. We have a high SNR signal, and it has to command the gains to start lowering the gains. The first step is to lower the gain at the RF stage, and then continue to adjust the gains at the baseband stage in order to bring the RMS at the A to D output into a target RMS value. So in this diagram, initially throughout the high gain setting, when the receiver is set to the highest gain and we have a low signal to noise ratio, low input power, the signal noise ratio increases as the signal power increases. However, the gain is constant, but as the signal noise ratio starts to increase beyond a certain point, we have to start peeling off the gain in order to avoid saturation and meet our target RMS value. In this case, the RF variable gain kicks in and we reduce the RF front end gain, and then we start adjusting the baseband variable gain amplifiers in order to meet our target RMS at the output of the A to D, or consequently at the input of the A to D. Here is a diagram that shows that as the RF input power increases, the ADC input power increases. We have a target power level we're trying to achieve, and at a certain point we have to detect that we exceed a certain threshold, and we go into what you call a nonlinear operation. In a nonlinear behavior, the actual gain at the RF front end is reduced and then we start adjusting the gain with the baseband VGAs. And there's a few steps when the SNR actually exceeds another threshold where we go into the nonlinear behavior and then revert back through the gain stages into linear behavior. The whole idea is to meet a target RMS value at the input of the A to D. Here we show 4 important curves that go a long way to explain how AGC works and how we can achieve a wide dynamic range using AGC, where the AGC control is in the baseband digital signal processor with interactions to the analog front end. First of all, the x-axis shows the relative RF input power in dB. The first curve shows the packet error rate, or actually in this case the bit error rate, versus the input signal power. Now if the input signal power is very small, very low, then the SNR is very low, and we get, this is for a particular fixed rate. When the signal noise ratio is very low, obviously we'll have a lot of packet error rates. We'll have a lot of errors, so the bit error rate will be very high. As the input signal power increases, the SNR will increase, and there'll be a certain point where we're able to decode the packet and the bit error rate will be very small. During this region, also the AGC kicks in, and we're able to operate over a very wide dynamic range. For example, as we mentioned before, around a dynamic range of 62 dB. As the signal noise ratio increases, as the input power increases, there'll be a point where the AGC control mechanism cannot peel off enough gain, and the signal power would be large enough in order to saturate the amplifiers in the baseband analog and also saturate the A to D. And at this point, beyond a certain signal power level or at very high SNRs, again the bit error rate will be very large and we lose packets. This is typically referred to as the bathtub curve and shows the AGC in action, where we achieve a wide dynamic range with the AGC and using, of course, a fixed number of bits in the A to D. And throughout this process here, the actual gain at the RF is being reduced, and the gains in the VGA are being changed in order to meet the target RMS value in order to achieve our bit error rate performance requirements. In this curve here, we actually show what is going on with the high gain in the RF front end part. So here we have the RF VGA, and it actually has 2 states. One is either high gain or low gain. For highest sensitivity, we initially set the RF front end at the highest possible gains and also the baseband amplifiers at the highest gain. And as the signal to noise ratio increases, we see that we're in the high gain, and at a certain point we begin to exhibit saturation, and the baseband AGC control will detect this, that the RMS has exceeded a certain threshold, and instruct the RF variable gain to actually switch to the low gain, and this is what we see over here. Also, we notice that the VGA, baseband VGA gain setting is also changing, and we had the range between -8 dB and +8 dB in 2 dB steps, and we see that the VGA starts to kick in order to adjust the gain so that we can meet our target RMS value. At a certain point, when the signal power is too large, then we actually have saturation and the bit error rate goes high. So this set of curves illustrates the operation of AGC in order to achieve a wide dynamic range in, for example, 802.11a or 802.11g. This curve here shows the estimated signal power in dB, and there's a range where AGC is performing correctly that we can actually estimate the signal power as the signal power increases. We're also tracking the estimated signal power, or RSSI in this case, and after a certain point, of course, in these regions where we have then saturation at the high end is where we're actually not in the operating mode, and our received sensitivity levels would be within this range over here. So in these ranges, obviously we cannot estimate the signal power, but in the range in between, given the AGC settings, the baseband will be able to form a correct estimate of the input signal power, which is actually required by the MAC layer. One of the issues with direct conversion receivers or zero IF receivers or Heterodyne receivers is of course IQ mismatch, and that occurs partly because of the fact that the synthesizer produces a in-phase and quadrature-phase term which could be offset by a certain phase, for example theta, and they could have a gain difference between the in-phase and quadrature phase, which we represent by epsilon, and also the fact that the in-phase receive chain could have a different gain than and the quadrature receive chain could have a different gain from the in-phase, and that can also lead to IQ imbalance. The factor of 2 over here is just for convenience, but if we do consider that the quadrature term has a phase difference of theta and the gain difference is epsilon, then when we demodulate the signals back to baseband, we get the baseband signals shown here, and we see that of course we're assuming that the carrier frequencies are matched, and at baseband we obtain the in-phase and quadrature phase terms. Now in the case where theta is equal to 0, that is, there is no phase difference, then this term here drops out and we get A, cosine becomes gone, and we just get A with a gain distortion. And for the quadrature term we also get B with a gain distortion as this term drops out, so this makes sense. And of course if epsilon is equal to 0, we still have IQ mismatch because of the phase difference. IQ mismatch is usually expressed in terms of the gain mismatch in dB and the phase difference in degrees. These diagrams, due to Behzad-Razavi, show the gain error effect on the constellation for QPSK. We have the ideal QPSK constellation points, and here are the constellation points due to a gain error. The constellation points due to a phase error are shown over here, and obviously in both cases IQ imbalance causes deviation. It will increase the EVM and degrade performance. This curve here is very instructive. It shows the performance of the symbol error rate versus EVN 0. This is from Shafi'i and Fouradi-Far's paper back in 2003 on the calibration of IQ imbalance. The curve over here is for the case where there is no IQ imbalance or it has been corrected, and the curve at the top is for the case where we do have IQ imbalance, in this case 5 degrees phase imbalance and half a dB gain imbalance. And obviously you see that as the signal noise ratio goes up, whereas the symbol error should continue to go down, we get a situation where there's a big difference in performance due to IQ imbalance. So it is clear that IQ imbalance has to be compensated for. Over here we show the compensation for IQ imbalance, assuming that the gain imbalance and the phase difference error have been estimated, and then using these operations we can actually eliminate it and remove IQ imbalance. Refer to the paper on how to estimate epsilon and theta, and of course one of the ways is to actually input a known source into the RF front end and then do the computations in order to estimate epsilon and theta, and there are other ways of achieving it using the long symbol processing. Here's a nice result from Broadcom in which they actually manufacture a transceiver, a CMOS transceiver using direct conversion architecture at 5 gigahertz, and a simple block diagram is shown over here. We see the direct conversion receiver and the direct conversion transmitter. A couple of interesting performance metrics here. First of all, they have a noise figure of 4 dB, which is very low, and total RX sensitivity at 6 megabits per second, which is minus 93.7 dB, which exceeds the IEEE 802.11a recommendations by about 10 dB, and also the receive sensitivity at 54 megabits per second beats the recommendation. The RX gain range is from 15 to 93 dB, And as we've discussed in 802.11a, you need a wide dynamic range in terms of gain, at least 62 dB. And the transmit power ranges from minus 30 dBm to plus 18.7 dBm. And the transmit 1 dB compression point is at 19 dBm, and other parameters. So in general, we can show other examples of direct conversion CMOS RFIC chips that have been developed for 802.11a and also for 802.11g at 2.4 gigahertz. And a lot of them actually exceed the recommendations provided by the IEEE 802.11a in terms of performance. One other thing is that many of these direct conversion receiver architectures use different ways in order to combat DC and combat IQ imbalance and other issues. I will refer you to the various IEEE publications and other publications so that you can actually look at the various architectures and the various trade-offs, and especially look at the architectures that use heterodyne versus homodyne or direct conversion.